The office is quiet this evening. Just a thin layer of lamplight and air between me and the dark. The distant city breathes faintly through the window, a soft glow wrapped in its own haze. On my desk, a single lamp turns the room into a little planet, bright at the centre, fading to shadow at the edges, like a tiny atmosphere held in place by paper and gravity. On the desk in front of me is a new case file, a thick, overstuffed folder, the kind that never quite wants to close. Across the front, in careful, slightly smudged handwriting, it says, Exoplanet atmospheres and possible biosignatures. It's a fancy way of saying we're trying to read the skies of other worlds and ask a gentle, stubborn question. Could there be life there? Good evening and welcome back. For those who don't know me, I'm Madeline Rowe, astrophysicist-turned-private-eye. Tonight I'll be your guide through this late-night case file in alien air. We'll move slowly, tracing the thin veils of gas wrapped around distant planets, listening for the faintest hints that something living might be stirring below. Now, as a quick aside, if this kind of calm, deep space storytelling helps you rest, you can tap subscribe or follow, just so you can find your way back here next time. But you absolutely don't have to. This corner of the universe is not a to-do list. It's just a quiet place to let your thoughts slow down. If you drift off halfway through, that's not a problem. That's the whole point. You don't need to remember the names of molecules or how the telescopes work. You don't need to keep up with every step of the investigation. You can let the details blur at the edges, the way a distant city does through a rainy window. I'll keep walking the case forward, whether you're wide awake or already halfway to dreaming. Okay then, let's start with something familiar. Something you've been living inside your whole life, even if you rarely think about it. An atmosphere? From the ground, it feels like empty space. Just air. Just nothing. But from a little distance, if you could pull back and look at Earth suspended in the dark, you'd see a thin, fragile halo of gas clinging to the planet. A soft blue gradient pinned in place by gravity, turning sunlight into sky. Every atmosphere is a kind of compromise, a negotiation between the pull of gravity, the heat from a star, the chemistry of rocks and oceans, and the restless dance of gas molecules themselves. Too little gravity, and the lightest gases escape into space like a slow leak. Too much heat, and even heavier molecules can drift away over billions of years. Too much volcanic outgassing, and the air can thicken into a dense, choking blanket. On some worlds, the atmosphere might be a deep, hydrogen-rich envelope, light gas piled up into a giant, puffy cloak around a small, rocky core. On others, the air might be razor-thin, a wisp of carbon dioxide, barely enough to whisper across the surface before the cold of space steals most of it away. You can imagine a little gallery of worlds, each one under a glass dome in your mind. One is wrapped in a thick, steamy blanket, cloud tops glowing where starlight strikes. Another is bare and sharp, its sky a faint, pale veil that the surface almost pokes through. Another is hazy orange, its air filled with complex molecules that turn light into fog. These are not just decorations. An atmosphere is a planet's interface with the universe. It decides how much starlight the planet absorbs, how fast heat leaks away at night, how liquids behave on the surface, and how any potential life might breathe or shelter or hide. On Earth, The atmosphere sits in a delicate balance. Nitrogen makes up most of the background. Oxygen takes the starring role for complex life like us. A shifting mix of water vapor, carbon dioxide, ozone, methane, and other trace gases flows through slow planetary cycles. Underneath all of that, the solid Earth and the oceans are in conversation with the air. Volcanoes vent gases upward. Rocks take them back again. Oceans dissolve them. Ice caps lock them away for a while, then release them as the climate shifts. On an exoplanet, far away and invisible to the naked eye, all of those same conversations might be happening quietly. But we don't get to stand on its surface. We don't get to taste the air, or watch clouds roll in, or feel the weight of the sky on our skin. All we get is light, just the way a star's glow changes, very slightly, as a planet moves through it. Imagine a distant star as a kind of cosmic lantern. It shines with a steady glow, a quiet, constant brightness when nothing passes in front of it. Now place a small, dark planet in orbit around that star. Every so often, from our point of view, the planet slides across the star's face, blocking a tiny fraction of the light. The star seems to dim by the smallest amount. That's a transit. If you could zoom in on that transit with perfect instruments, you would notice something subtle. When the planet is directly in front of the star, some of the starlight has to pass through the thin ring of atmosphere around the planet's limb. It skims through the upper layers of gas before reaching your telescope. Different molecules in that atmosphere will absorb different colours of light. Water vapour might nibble away at certain infrared wavelengths. Methane might carve little notches in another part of the spectrum. Carbon dioxide might leave its own characteristic dips. If you split the star's light into its component colours, like stretching a rainbow into a long, detailed barcode, you would see those missing pieces. Narrow, dark lines, where the planet's atmosphere has removed light. This is transmission spectroscopy, reading the silhouette of an atmosphere, not by seeing it directly, but by noticing how it edits the light passing through. There are other tricks too. If the planet glows in its own thermal light, perhaps because it's very hot, we can watch what happens when the planet slips behind the star, hidden from our view. The total light we see drops ever so slightly because we've lost the planet's contribution. By comparing the before and after, we can infer something about the planet's own emission. We can do similar comparisons as the planet moves through its phases, from crescent to gibbous to full. We watch how the reflected starlight changes with angle and how different wavelengths brighten or fade. At the heart of all these methods is the same idea: a spectrum. A spectrum is like a fingerprint or a barcode or a line of music notes, depending on which metaphor you like best. Each molecule has certain energies it can absorb or emit, tied to the ways its atoms can vibrate or rotate. Those energies correspond to very specific colours of light. When we look at light from a star passing through a planet's air, we're effectively holding that air up to the light and asking which colours are missing, which notes are quiet, which bars in the code have gone dark. From that, with enough patience and careful modelling, we can reconstruct something about the atmosphere. What gases are there? Roughly how much? And how they might be layered. We can't see the sky directly, but we can read its imprint. Before we go flinging ourselves across the galaxy, it helps to look at a world we know by heart, our own. If you could fly a telescope far away from Earth and look back at our planet as if it were an exoplanet, you would see a pale, bright disk, mottled with clouds and oceans and continents. But if you took its light and spread it into a spectrum, you'd see much more. In the infrared, you'd find deep absorption features from water vapour, telling you that this world has active water in its air. You'd see carbon dioxide shaping the greenhouse effect. You might pick up ozone, a fragile layer high in the stratosphere, formed from oxygen and sunlight. In the visible and near-infrared, you'd notice a curious pattern. The way the reflectivity changes around a particular red wavelength. A feature called the vegetation red edge. It comes from the way plants on Earth absorb and reflect light. They absorb strongly where the sun's output is high, and reflect more in the near-infrared, bouncing back what would overheat them. If you tracked Earth over time through its seasons, you'd notice subtle variations. Carbon dioxide rising and falling with plant growth, snow and ice advancing and retreating, clouds shifting with weather patterns. Our planet's spectrum is not static. It's alive with cycles. One of the most striking things about Earth's atmosphere, from a distant chemical perspective, is that it's out of balance. Oxygen is extremely reactive. Left alone, it tends to combine with rocks, with dissolved iron, with gases like methane, with almost anything it can oxidize. And yet, on modern Earth, oxygen makes up about 21% of the atmosphere. Methane is also present, not in huge amounts, but enough that it shouldn't last long if there were no source replenishing it. From a purely chemical point of view, this mixture looks strange, as if some continuous process is working away, splitting water, fixing carbon, and sending out these gases as byproducts. On Earth, that process is life. Photosynthetic organisms, from tiny cyanobacteria to towering forests, breathe in carbon dioxide and water, and breathe out oxygen. Other microbes produce methane. Over billions of years, Earth's atmosphere has changed dramatically. There was a time, early on, when there was essentially no oxygen at all, and the air was rich in carbon dioxide and other gases. There were epochs when organic hazes may have wrapped the planet in a golden or orange veil, changing how it looked from space. If you'd observed Earth in those eras from light years away, you might not have recognized it as inhabited, even though the oceans were already teeming with microscopic life. Our own planet reminds us that life and obvious biosignatures are not the same thing. Sometimes the atmosphere tells a clear story. Sometimes it whispers, sometimes it hides its secrets altogether. When scientists talk about biosignatures, they're looking for things that life does that are hard to explain any other way, especially when you consider the whole context of a planet. Some of those signals are gases in the atmosphere. Some are patterns in how the light from a planet changes over time. Some are colours or spectral features from the surface. None of them exists in isolation. Let's start with gaseous biosignatures. A gaseous biosignature is a molecule or a mix of molecules in a planet's air that is hard to maintain at that level without ongoing biological activity. Oxygen, as we've already seen, is an obvious example on Earth. In a purely geological atmosphere, you might expect some oxygen from processes like the splitting of water by sunlight, followed by the escape of light hydrogen to space. But large amounts of oxygen over billions of years on a temperate, water-rich world start to look suspicious. Methane can also be a biosignature, but it's trickier. On Earth, much of the methane in the air comes from microbes, from wetlands, from the guts of animals. But methane can also be produced geologically, in reactions between rock and water, or from volcanic activity. What becomes interesting is when certain gases coexist in amounts that don't make sense in equilibrium. Large amounts of both oxygen and methane, for instance, suggest that something is constantly replenishing both, fighting against the tendency of these molecules to react and disappear. There are other candidate gases too. nitrous oxide produced by microbes in soils and oceans, certain sulfur containing compounds, halogenated gases that, on Earth, are mostly industrial. Each one has to be examined in context. Could this be made by life? Could it also be made in large amounts by non-biological chemistry? How long would it last in the atmosphere before sunlight or reactions destroyed it? Then there are surface biosignatures, patterns in the way a planet's surface reflects light that might be explained by widespread light-absorbing pigments. On Earth, the vegetation red edge is one such feature. Plants absorb visible light efficiently for photosynthesis. Then their reflectivity jumps in the near-infrared, producing a characteristic step in the spectrum. On another world, under a redder or bluer star, life might settle on different pigments, tuned to different wavelengths. The planet might show a strong edge somewhere else, or even a very different colour palette. Purple, rust red, deep black, metallic shimmer, all hypothetical but grounded in the idea that life will adapt to whatever light it has. Finally, there are temporal biosignatures, changes over time. Maybe the spectrum of a planet's atmosphere shows seasonal breathing, as gases rise and fall with a biological cycle. Maybe the brightness of certain wavelengths tracks something like vegetation growth, snowmelt, or plankton blooms in a pattern that repeats with the planet's orbit. Detecting these on a real exoplanet would be extremely challenging. It might require years of careful observations, watching the same world turn and orbit again and again. But in principle, they're part of the toolkit, not just what's in the atmosphere, but how it moves through time. All of these categories overlap. A gas might be both a potential biosignature and a key player in climate. A surface pigment might only really make sense in combination with a particular atmospheric composition. A seasonal signal might only be interpretable if you already know something about the planet's tilt and orbit. So instead of thinking of a single lifeline in a spectrum, it's better to imagine a web of clues. Lots of small pieces of evidence that, taken together, might persuade you that life is the simplest explanation. When researchers propose a new biosignature gas, they don't just write its name down and walk away. They have to put it on trial. In the lab and in models, they ask a series of quiet, persistent questions. Could life plausibly make this molecule in large quantities? Could it build up to detectable levels in a realistic atmosphere? Or would it simply dissolve into an ocean, or react quickly with other gases? Or freeze out on the night side? They look at how the gas interacts with light, which wavelengths it absorbs, how strongly, what kind of spectral fingerprint it might leave. Then they place that fingerprint against the backdrop of the planet's star. A molecule that looks dramatic under sunlight might be much harder to spot under a dim red dwarf, or vice versa. They also compare biological sources to abiotic ones. For some gases, geology or atmospheric chemistry can churn out large amounts without any biology at all. For others, the non-biological pathways are weak, slow, or require very special conditions. The best candidate biosignatures are those where life has a clear, efficient way to produce the gas, and where non-living processes struggle to compete, especially on planets with certain temperatures, pressures, and compositions. In some recent work, scientists have gone through lists of potential gases systematically, especially molecules with certain functional groups or chemical behaviours. They test them in detailed models of terrestrial exoplanet atmospheres. They simulate sunlight of different colours, varying levels of background gases, different ocean coverages and surface types, and track how each candidate behaves. Sometimes the result is encouraging, a gas that is stable enough to accumulate, distinctive enough to detect, and hard to produce in bulk without biology. Other times, the verdict is more disappointing. The gas dissolves easily in water, or reacts away quickly with oxygen, or is produced so readily by photochemistry that its presence is ambiguous. Those molecules may still matter for climate or haze formation, but they're less useful as clean biosignatures. It's slow work, a mix of chemistry, planetary science, and imagination, all grounded in the stubborn requirement that whatever we call a biosignature has to survive contact with physics. Of course, even the best candidate gases come with a warning label. Beware of false positives, and beware of false negatives. A false positive is a signal that looks like life, but isn't. For example, certain dry carbon dioxide-rich atmospheres around stars with strong ultraviolet light can build up oxygen and ozone even without biology. Water gets split by energetic photons, the light hydrogen escapes to space, and the heavier oxygen lingers. If you only saw the oxygen and ozone, you might be tempted to declare victory. But if you also knew the planet had little surface water, or that its climate and photochemistry favoured this abiotic build-up, you'd think twice. On the other side are false negatives, cases where life exists, but the atmosphere doesn't shout about it. Maybe the biosphere is small and slow, its gases constantly mopped up by rocks and oceans. Maybe thick clouds or hazes hide the spectral features underneath. Maybe the dominant metabolism doesn't produce any strong, volatile gases at all. Early Earth again is a sobering example. For long stretches of its history, life was present and active, but the atmosphere may have looked relatively unremarkable from afar, especially if your instruments were limited. To navigate between these pitfalls, scientists talk about a weight of evidence approach. Instead of treating any single molecule as a smoking gun, they try to build a layered case. They look at the star, its type, its age, its ultraviolet output. They estimate the planet's mass, its radius, and how much energy it gets from its star. They run climate models to see which atmospheric states are stable. They consider volcanic activity, photochemistry, water loss, and other abiotic processes, and ask whether any of these can explain the observed spectrum. If not, they ask whether adding life makes the picture simpler or more contrived. Only when multiple lines of evidence point in the same direction does the idea of a living planet start to feel compelling. And even then, the language stays careful. Potential biosignatures. Compatible with biological activity. Difficult to explain abiotically under known conditions. Somewhere in the data streams from our telescopes, there may already be a spectrum from a planet whose atmosphere is quietly unusual. A world with water, clouds, and a mix of gases that don't quite sit still in chemical equilibrium. In the years ahead, as new observatories come online, as models improve, as we learn more about stars and planetary systems unlike our own, some of those strange spectra will move from the curious pile into the seriously interesting pile. One day, we might have a planet where the weight of evidence is heavy. Water in the air, clouds in a temperate climate, gases in persistent disequilibrium, seasonal variations that line up with a plausible biological cycle. No single feature definitive, but the whole picture leaning toward life. When that happens, there probably won't be a single dramatic, universe-shaking moment. No headline that reads, "Case closed." Instead, there will be papers, and follow-up observations, and more papers, careful arguments stretching out over years. But for most of us, it won't matter whether the verdict is stamped this decade or the next, or the one after that. What matters is the quiet shift in perspective. The knowledge that we can look at a distant point of light, pass its colours, and glimpse the chemistry of a faraway sky, not as an abstract calculation, but as a possible home for life. Tonight, you don't have to carry any of that weight. You can let the thought of alien atmospheres drift to the edges of your mind, like thin clouds around a dark planet. You can imagine distant worlds turning slowly in their orbits, their skies glowing softly in colours you'll never see directly. The case file will still be here tomorrow, still open, still full of spectra and questions. For now, you can set it down. Let your breathing fall into a slow, easy rhythm, and let sleep come find you in its own time. If you're somehow still awake, we can open a few extra folders, side cases inside the main investigation, classic biosignature gases, new candidate molecules, strange coloured planets, and the telescopes that watch them. Before we open the folders on individual gases, it helps to step back for a moment and look at the whole cabinet. There isn't just one kind of exoplanet atmosphere out there. Astronomers talk about an exoplanet zoo, a spread of worlds from giant, star-hugging hot Jupiters down to cool sub-Earths, each under very different skies. You can picture a long shelf of glass globes, each one lit from within by a different star, each with a different thickness and colour of air. Some of the knobs that shape those skies are simple to name, even if they're hard to measure. Gravity, temperature, the basic mix of elements the planet had to work with, how much hydrogen and helium it managed to hang on to, and how fiercely its star bathes it in high-energy light. A planet with strong gravity and a thick blanket of hydrogen and helium will tend to keep a light, extended atmosphere. The same planet with less hydrogen to work with, or with billions of years of hydrogen peeling away to space, may end up with an atmosphere dominated by heavier molecules instead. Water vapor, carbon dioxide, nitrogen. Change the overall hydrogen budget, and you change which molecules are easy to make and keep. Change the temperature, and you change which of those molecules are stable in the gas phase and which prefer to condense out into clouds or ices lower down. The ratio of carbon to oxygen matters too. Worlds with roughly solar-like proportions tend to divide their carbon and oxygen between familiar species like water, carbon monoxide, carbon dioxide, and methane. Shift the balance toward much more carbon, and you can tilt an atmosphere toward carbon-rich molecules, hydrocarbons, nitriles, even soots, and graphite-forming clouds. Shift the balance the other way, toward more oxygen and less carbon overall, and you open the door to skies where water and carbon dioxide dominate, or even oxygen itself, if hydrogen has been slowly lost. On smaller, denser planets, super-Earths, and rocky worlds, the story gets even more tangled. Some of their air comes from whatever light gases they grabbed from the disk early on. Some comes later from outgassing, volatiles released from the interior as the mantle melts and cools. Some of it can be stripped away by impacts, or by strong stellar winds and high-energy radiation. Over time, those processes can leave two planets with similar sizes and orbits under very different skies. One with a hydrogen-rich envelope, another with a compact atmosphere dominated by water, nitrogen, or carbon dioxide. From far away, we don't see all of that history directly. We just see the end result. Which molecules are present, how thick the air is, how tall the scale height is when a planet crosses its star. But in the background of every spectrum is this quiet set of controls: gravity, temperature, elemental mix, hydrogen content, stellar radiation, all of them nudging the chemistry in one direction or another. Anytime we talk about biosignatures, we're layering biological possibilities on top of those basic planetary settings. Life, if it's there, has to work with whatever sky it inherits. Even once you've dialed in those basic planetary knobs, atmospheres don't sit in perfect chemical balance forever. Light stirs them. Mixing stirs them. Planets are not test tubes. They're more like slow-moving kitchens. Deep down, where pressures and temperatures are high, chemistry tends toward equilibrium. Elements sort themselves into the combinations that are most stable for those conditions. Higher up, closer to space and starlight, things are messier. Ultraviolet photons split molecules apart. Vertical motions bring gases upward faster than they can re-equilibrate. On hot Jupiters that circle very close to their stars, the upper atmosphere is flooded with energetic light. Water vapor can be broken apart into hydrogen and oxygen atoms. Methane, if it's present, can be chopped into fragments that try to build larger hydrocarbons, only to be broken again. Models show that this combination, high temperatures, strong ultraviolet light, and abundant water, makes it surprisingly hard for complex hydrocarbons to survive in large amounts. They start to form, then get quickly destroyed. Instead of building a rich orange haze like the one over Jupiter or Saturn, the air stays relatively clear, and a large reservoir of free hydrogen accumulates high above the planet. That hydrogen can help feed an extended upper atmosphere, even an escaping tail of gas reaching out into space. On cooler gas giants, the balance shifts. The same ultraviolet light still breaks methane and other molecules apart, but the temperatures are lower, and some of the reaction pathways slow down. Hydrocarbons like acetylene and ethane can survive through a wider range of altitudes, shaping the planet's mid-infrared spectrum and providing efficient ways for those upper layers to cool. Photochemistry also generates radicals, highly reactive fragments like OH, that act as intermediates on the way to other molecules. They can slowly build up oxidized products such as nitrogen oxides and molecular oxygen in some regimes. All of this happens whether or not anything living is present. From a distance, it just looks like an atmosphere refusing to stay in simple equilibrium. For biosignatures, that means we have to account for this background of disequilibrium chemistry. If we see a surprising molecule, we first ask, could photochemistry and vertical mixing on this planet, under this star, make and maintain it without any help from biology? Sometimes the answer is yes. Sometimes the answer is no, at least not easily. Sometimes the answer is a long, cautious maybe. But either way, the fingerprints we read are always written by a combination of deep, slow chemistry, fast reactions in the light, and whatever stirring motions move gases between those regimes. Then there are the clouds. On Earth, cloud usually means water droplets or ice crystals. On exoplanets, the word stretches. High above some hot, giant planets, temperatures are so extreme that clouds may be made of silicates, rocky compounds that would be part of sand or stone in a cooler environment. Elsewhere, droplets of molten metals or metal sulfides may condense. On smaller, cooler, hydrogen-rich worlds, super-Earths, and mini-Neptunes, the menu expands again. Equilibrium models suggest that as you move from very hot upper atmospheres down into cooler layers, different condensates peel out of the gas. Aluminum and titanium-bearing oxides and silicates at the highest temperatures. Then iron and magnesium silicates, then more exotic salts such as zinc sulfide and potassium chloride. Farther down, where it's cold enough, you can get clouds of water, ammonia, or even methane ice. The amount of heavy material in the atmosphere, the metallicity, matters here as well. With only solar-like abundances of heavy elements, some of those clouds may be quite thin, with only a small total mass available to condense. Increase the metallicity by factors of hundreds or more, as is plausible for some sub-Neptunes, and those same compositions can produce thicker, more optically important clouds. They can even flatten out a planet's transmission spectrum, turning what might have been a forest of spectral lines into something almost flat. On top of the equilibrium condensates, photochemistry can build hazes. When ultraviolet light breaks apart methane, nitrogen-bearing species, or other molecules, the fragments can eventually polymerize into complex organic particles, soots, that float high in the air. If the atmosphere is metal-rich and carbon-rich, graphite itself can condense, forming dark clouds that absorb light efficiently. Other compositions, like alkali salts, may join the mix on certain worlds. From a distance, all of those possibilities blur into a simple observational fact. Sometimes, when a planet passes in front of its star, we see deep, sharp absorption features from gases in a clear atmosphere. Sometimes we see shallow, muted features, as if we're peering through a frosted window. And sometimes we see almost nothing at all, a flat line that says clouds and hazes without telling us much more. For biosignatures, clouds are both obstacles and clues. They can hide the very gases we most want to detect, masking oxygen or methane or water features. But their presence, altitude, and variability also feed into our picture of a planet's climate. A world wrapped in thick, reflective clouds might be cooler at the surface than its orbit alone would suggest. A hazy world might have complex photochemistry that has to be understood before we can interpret any potential biological gases. Either way, when we look at a spectrum and see missing information, we remind ourselves that some of the story might simply be locked behind unfamiliar weather. Atmospheres don't just sit and simmer. Given enough time and enough stellar energy, they can leak. Close to their stars, many giant planets live under an intense bath of X-ray and ultraviolet light. Those photons heat the upper atmosphere, pushing it toward temperatures where the gas can expand and flow outward. High above the visible cloud tops, molecules are broken apart into atoms and ions. At those altitudes, diffusion and escape sort particles, not only by chemistry, but by mass. Hydrogen, being light, reaches the highest levels and is the first to spill outward. If the flow becomes strong enough, it can drag heavier atoms along with it in a hydrodynamic wind. Observations of some hot Jupiters show signatures of extended escaping atmospheres. Hydrogen reaching far beyond the planet's nominal radius, and in some cases, heavier elements and ions showing up as broad, deep absorption during transits. In a few especially irradiated systems, helium has been detected streaming away in long tails that trail behind the planet or even wrap partway around its orbit. From a distance, those planets look almost comet-like, losing parts of their primordial envelopes to space. On smaller worlds, where gravity has less of a grip and the atmosphere may already be relatively light, cumulative escape over hundreds of millions or billions of years can transform the sky more fundamentally. A young super-Earth or mini-Neptune might start with a generous hydrogen-helium envelope. As high-energy radiation from the star eats away at the top, that envelope thins. What's left behind is a denser atmosphere enriched in heavier molecules, or in some cases, almost no atmosphere at all. The overall metallicity goes up as hydrogen is lost, and any gases outgassed from the interior, water vapor, carbon dioxide, nitrogen, sulfur species start to play a larger role. The end result is that two planets with similar sizes can wind up in very different categories. One might remain a puffy, low-density world with a thick hydrogen cloak. Another might compact down into a denser super-Earth with a heavy, high mean molecular weight atmosphere. When we search those skies for biosignatures, we're seeing the outcome of both formation and erosion. How much gas the planet captured early on, and how much it was able to keep. A stable, long-lived atmosphere that can hold liquid water at the surface for billions of years is a kind of quiet prerequisite for complex life as we know it. Escape doesn't make that impossible, but it does mean that some worlds that started off promising may have shed their envelopes long ago. Most of the time tonight, we've treated spectra as smooth curves, broad bands, and gentle dips. In reality, when you look closely enough, those bands are made of thousands of narrow lines. Each one comes from a specific transition in a specific molecule or atom. High-resolution spectroscopy is what happens when you spread the light out finely enough to see those individual lines, or at least feel their combined pattern. Instead of dividing light into a few dozen or a few hundred colour channels, you divide it into tens of thousands. From the ground, large telescopes feed that light into instruments with resolving powers of 50,000 or more. At that level of detail, telluric features from Earth's own atmosphere and absorption lines from the host star can be modelled and peeled away. What's left, buried deep in the noise, is a forest of planetary lines, each Doppler shifted as the planet moves in its orbit. On any single wavelength channel, the planet's signal is too faint to see. But the pattern of lines is known from models of the molecule's spectrum. Observers slide that template back and forth in velocity space, stacking contributions from all the lines at once. When the template lines up with the data, the combined signal adds up into a detectable peak. Do this for a sequence of observations taken through the planet's orbit, and you can watch that peak trace out the planet's changing radial velocity as it swings around its star. In plots that map out the strength of that combined signal as a function of assumed orbital speed and system velocity, the planet appears as a bright, focused spot where all the assumptions line up. Elsewhere, the diagram is mostly noise and weak structures, a backdrop of no planet here. With this technique, high-resolution spectra have revealed rich atomic and molecular content in the hottest, most irradiated planets, lines from neutral and ionized metals, from carbon monoxide, water, and other species in their glowing daysides. Subtle shifts and broadenings of the lines carry information about winds and rotation, day to night side flows that blow hot gas around the terminator, or signatures of how fast the planet is spinning on its axis. In some cases, extended helium tails and escaping material have been traced in velocity space, giving us direct clues to atmospheric loss. As new telescopes come online with even larger mirrors, especially the extremely large telescopes under construction, this kind of work will push toward cooler and smaller worlds. The jump in collecting area means that spectra that once took many nights to accumulate will be reachable more quickly, or for fainter targets. High-resolution studies may be able to peer above clouds and hazes that flatten out lower-resolution transmission spectra, seeing lines from gases higher up. They may also help disentangle the subtle effects of star spots and stellar activity that can otherwise masquerade as or confuse planetary signals. For our purposes, all of that detail is another layer in the same long, patient story. We start with the simplest measurements, a dip in starlight when a planet crosses in front, or a small change in total brightness when it slips behind. Then we add colours and see which wavelengths are missing. Then, in some regimes, we add the fine structure of high-resolution lines, letting us sense winds, rotation, escape, and even isotopes. All of it is just light, spread thinner and thinner, until what began as a single point in the sky turns into a surprisingly detailed case file. By the time you hear about a planet with measured winds or escaping helium, a whole chain of these techniques has already done its work in the background. You don't have to keep track of how each one functions. It's enough to know that when astronomers say quietly, "We've seen this gas in that atmosphere," or "We've measured the speed of those upper winds," they're speaking for armies of photons, counted carefully over many nights, and sifted through methods built to listen to atmospheres in finer and finer detail. First, the classic case files. Old familiar suspects in the biosignature lineup: oxygen and ozone. On modern Earth, oxygen is everywhere. In the air you breathe, in the water you drink, in the rocks beneath your feet. It's so ubiquitous that it's easy to forget how strange it really is, chemically speaking, to have that much of it floating free in the atmosphere. For a long time, Earth's air had little to no oxygen. Microbes lived their lives using other electron donors and acceptors, cycling sulfur, iron, and carbon in ways that didn't produce a sky full of O2. Then, slowly, through the rise of oxygenic photosynthesis, the balance changed. Tiny organisms began to split water using sunlight, releasing oxygen as a byproduct. At first, the oxygen was soaked up by reduced minerals, oxidizing iron and other elements. But over time, those sinks filled, and oxygen began to accumulate in the air. From far away, a high oxygen content atmosphere is a striking signal. It suggests that either some relentless non-biological process is at work, or that a biosphere is tirelessly producing O2 and keeping it there. Ozone, made of 3 oxygen atoms, is a secondary player in this story. Formed high in the atmosphere where ultraviolet light splits O2 and lets it recombine, the ozone layer shields the surface from harsh UV radiation. In spectra, ozone has its own distinct features, a kind of echo of oxygen's presence. But oxygen and ozone are not perfect witnesses. There are scenarios, especially on very dry planets, where water photolysis and hydrogen escape can leave behind large amounts of O2 without any biology. In some cases, those abiotically produced oxygen atmospheres could persist for long timescales. So in the margin of this file, scientists scribble a note. Promising, but context-dependent. Check water inventory, check stars ultraviolet, check co-occurring gases. Next file, methane. On Earth, methane is a kind of quiet exhalation from life. Microbes in wetlands, in sediments, in the guts of animals, and in other low oxygen environments release CH4 as a waste product. Methane is a powerful greenhouse gas. It doesn't last very long in an oxygen-rich atmosphere. Ultraviolet light and reactive radicals break it down, returning carbon to other forms. Geology can produce methane too, in reactions between water and certain rocks, or from the outgassing of deep reservoirs. On icy satellites and cold worlds, methane can even act as a volatile, cycling between solid and gas phases like water does on Earth. So a detection of methane alone is ambiguous. On a small, warm, rocky planet with liquid water and other signs of habitability, methane at certain levels might raise eyebrows, especially if no obvious geological source can account for it. But paired with oxygen, or with other disequilibrium indicators, Methane becomes more powerful. The file on methane ends with a similar note, useful when part of a set, not decisive on its own. Another thin folder holds nitrous oxide and a few other niche gases. On Earth, nitrous oxide is produced largely by microbial processes in soils and oceans, tied to the nitrogen cycle. Its concentration in our atmosphere is small compared to nitrogen or oxygen, but significant enough that, with a sensitive enough telescope, it might be detectable from afar. Chemically, nitrous oxide is less easily produced in large quantities by non-biological processes, making it an intriguing biosignature candidate. But detecting it on an exoplanet would be challenging because its spectral features are subtle and can overlap with those of other gases. Similar stories play out for other trace gases, like certain sulfur compounds or halogenated molecules. On Earth, some are tied strongly to biology or even to industrial activity. On other worlds, the balance between biological and abiotic sources might be different. The classic gas files close with a gentle reminder. Small signals now, potentially telling in future higher precision spectra. One by one, these familiar cases file back into the drawer. Oxygen and ozone, methane, nitrous oxide and its friends. None of them is a single, definitive proof of life. Each is a clue, part of a pattern that might, in the right context, point strongly toward biology. For now, you can imagine those folders closing softly, the cabinets sliding shut with a quiet click as the office grows even more still. Somewhere else in the building, far from the telescope control rooms, there's a different kind of lab. Glassware, gas cylinders, spectrometers, and rows of computers humming in the background. This is where new candidate biosignature gases go to be tested. Not in the sky, but in careful simulations of sky-like conditions. Imagine a researcher, late at night, much like you, staring at a long list of molecules. Some look familiar, simple organics, small nitrogen or sulfur-containing species. Others are longer, with branching chains, rings, or unusual combinations of atoms. They're not chosen at random. Each is there because it could, in principle, be produced by metabolism, or by a pathway that life might favour on a world with different conditions than Earth. For each candidate, the researcher asks what would happen if this gas were produced by life at the surface. Would it stay in the gas phase? Would it dissolve quickly into oceans? Would it react with common atmospheric molecules like oxygen or carbon dioxide and vanish? In computer models, they build virtual planets. Rocky worlds with different surface gravities, different temperatures, different mixtures of background gases. One might have a nitrogen-rich air like Earth, another a thicker carbon dioxide-dominated blanket, another a hydrogen-rich envelope above a smaller core. They shine virtual starlight onto these worlds, with spectra tailored to different star types. Bright in the ultraviolet for sun-like stars, red shifted and gentle for cool M dwarfs, somewhere in between for K-type suns. Then they introduce the candidate gas, giving it a steady flux from the surface to represent biological production, and watch what happens. Some molecules are quickly broken apart by ultraviolet photons, their fragments reacting into other chemicals. Others are relatively stable, lingering in the middle atmosphere before eventually being removed. Some dissolve readily in liquid water, vanishing into oceans or lakes before they have a chance to build up in the air. Others resist dissolution, staying mostly in the gas phase. At the same time, spectroscopists examine how each gas interacts with light. They measure or calculate cross-sections, how likely the molecule is to absorb photons at different wavelengths. They look for distinctive bands, regions where the gas produces strong, recognizable features. A gas that is stable and abundant, but whose spectral lines are weak and easily confused with others, might be difficult to use as a biosignature. Another gas might have a sharp, clear fingerprint, but be so reactive that it never accumulates beyond trace levels. A promising candidate is one that finds a sweet spot. Life can produce it in enough quantity. The atmosphere lets it linger, and its spectrum stands out cleanly against the background. There is a kind of quiet artistry in all of this. It's not just about crunching numbers, but about understanding the interplay between chemistry, climate, and metabolism. Researchers think about the energetics of different reactions, the availability of elements, the likely byproducts of plausible alien metabolisms, all while keeping an eye on what a telescope would actually see. Some candidate gases survive this gauntlet with their promise intact. They end up on short lists of future targets for upcoming missions, the kinds of molecules we might hope to detect with next-generation instruments. Others are quietly retired from the biosignature conversation. They might turn out to be too easy to produce abiotically, or too fragile, or too easily hidden by more abundant gases. None of this means they are uninteresting. They may still shape the climate, influence cloud formation, or contribute to hazes. They may matter enormously for the internal workings of a planet's environment. They just aren't reliable as standalone signs of life. In the end, what remains is a carefully curated set of possibilities, each with notes pinned to it. Production pathways, destruction mechanisms, spectral regions of interest, warnings about lookalike signals. You can picture these notes scattered across a large corkboard, threads connecting gases to star types, to atmospheric compositions, to potential observational strategies. As you listen, you don't need to hold onto the chemical names or the details of every reaction. It's enough to know that behind each proposed biosignature lies a long chain of reasoning and testing, built to make sure that when we finally point to a distant spectrum and say, this might be life, we're doing it with as much care as we can. The lab lights dim. The last computer monitor goes dark. The list of candidate gases settles into a quiet, patient waiting. The sky will give up its secrets slowly, but the groundwork is already being laid, molecule by molecule. So far, we've stayed mostly in the air, in gases and spectra and invisible lines of chemistry. For a little while, let's come down toward the surface, to the boundary where light bounces off rock, ocean, and whatever might be growing there. When you look at Earth from space, you see blues, whites, greens, and browns. Blue from the oceans and from scattered sunlight in the atmosphere. White from clouds and ice. Green and brown from forests, grasslands, deserts, mountains. That green is not an accident. The plants that blanket so much of Earth's land surface are using pigments like chlorophyll to capture light. They absorb strongly in parts of the visible spectrum where the sun's output is high. They reflect more in the near-infrared, creating the vegetation red edge in the planet's reflectance spectrum. If you were an astronomer on another world with a powerful telescope trained on Earth, and you saw that distinctive step, you might suspect that something on the surface was tuning itself to the star's light and using it for energy. On other planets, under other stars, the palette might shift. Around a cooler, redder star, the available light is different. Less blue and ultraviolet, more deep red and near-infrared. Life, if it arose there, might choose pigments that look very different to us. Perhaps black surfaces that swallow as much light as possible. Perhaps deep purple or crimson, optimized for the wavelengths where that star shines brightest. Perhaps something we don't even have a simple name for, because no Earth organism quite matches it. From a distance, those choices would show up as changes in a planet's color. Where Earth's reflectivity jumps at one wavelength, an alien biospheres might jump somewhere else, or create entirely new patterns in the spectrum. Imagine a world where the continents are covered in dark, glossy vegetation, nearly black in visible light, but bright and mirror-like in the infrared. Or another where photosynthetic organisms live in shallow seas, turning the oceans into a rich, jewel-toned purple from space, with land remaining relatively pale. Clouds move over these surfaces, sometimes masking the underlying colour, sometimes revealing it in patches. Seasons come and go, shifting the balance between ice, ocean, and living pigment. If you could watch such a planet over months and years, you might see its integrated colour drift gently with its seasons, the way Earth's does, but with a different spectral signature. Researchers model these possibilities by building strange Earths in their computers. Versions of our world where forests are replaced with hypothetical alien plants, each with different pigment sets. They then calculate what the planet's spectrum would look like from afar, and how easy it would be to confuse those signatures with more mundane surfaces like rock, sand, cloud, or ocean. Some pigment choices produce very distinctive signatures, strong edges or peaks that stand out clearly. Others are more subtle, blending into the background enough that distinguishing them would require extremely precise observations. Underneath all this is a simple, almost poetic idea. Life reshapes the way a planet looks, not just in its spectra, but in its colours, its cloud patterns, its surface textures. On Earth, forests and phytoplankton and algae are part of the planet's visible identity from space. On another world, the equivalent organisms might stamp their own aesthetic on the globe. Whether we'll ever be able to see those details clearly is an open question. Instruments will need to be extraordinarily sensitive. Observations will need to be carefully planned and interpreted through the inevitable uncertainty. But even now, as we stare mostly at unresolved points of light, the idea that those points may conceal rich, varied surfaces is a gentle kind of comfort. The universe may be filled with worlds that are not just alive, but beautiful in ways we can barely imagine. As you picture those strange Earths, you might let the details soften, edges blurring, colours melting into one another, clouds drifting across continents without hurry. You don't need to hold any one image still. The planets can keep turning, slowly, in your mind, until they fade into something indistinct and peaceful, like the last thoughts before sleep. For our final stretch tonight, let's step away from the planets themselves and wander through the observatories that make all of this possible. These telescopes are the tools we use to turn faint, distant starlight into spectra and light curves, into case files on worlds we'll never visit. Picture a space telescope first. Floating high above the interference of Earth's atmosphere, it stares steadily at a patch of sky. Its mirrors cooled, its instruments tuned to catch photons that have been travelling for years. Some of these telescopes are optimised for the infrared, where the fingerprints of water, carbon dioxide, methane, and other key gases are especially strong. When an exoplanet passes in front of its star, the telescope records the tiny drop in brightness, again and again, transit after transit, building up a signal out of the noise. Later, on the ground, scientists split that time series by wavelength, measuring how the transit depth changes with colour. Those variations become the ingredients for transmission spectra, revealing atmospheric composition. Other telescopes perched on high mountaintops use enormous mirrors and advanced optics to peer through Earth's own air, correcting in real time for the turbulence that would otherwise blur the view. These ground-based giants can collect huge amounts of light, making them powerful tools for high-resolution spectroscopy and for studying the brightest, closest systems in great detail. In design studies and concept papers, future observatories are already taking shape on drawing boards and computer screens. Some are large, visible, and ultraviolet optimized space telescopes designed to directly image Earth-sized planets around nearby stars by blocking out the overwhelming glare of the host star with coronagraphs or star shades. Others are infrared interferometers, multiple smaller telescopes flying in formation, combining their light to achieve resolutions far beyond any single mirror. Still others are extremely large ground-based telescopes, with primary mirrors tens of meters across, capable of dissecting faint spectra with exquisite precision. Each of these instruments is imagined with specific questions in mind. Can we measure the atmospheric composition of a temperate rocky planet in the habitable zone of a nearby star? Can we detect water vapor, oxygen, ozone, methane, or other key gases in its air? Can we track seasonal changes, detect clouds, gauge surface pressure, or infer the presence of oceans? Can we distinguish between abiotic and potentially biotic sources for observed spectral features, given realistic uncertainties and limited observing time? The road ahead is long, and that's part of its quiet charm. Exoplanet science, especially the search for biosignatures, is a discipline measured in decades. Instruments must be designed, built, launched, commissioned. Data must be gathered slowly, painstakingly, over years. Models must be refined, cross-checked, and compared with observations. Along the way, surprises will arrive. Worlds with atmospheres we didn't anticipate, with clouds in unexpected places, with spectra that don't fit neatly into our categories. Each surprise will teach us something, even if it doesn't bring us closer to a definitive detection of life. For you, listening in the dark, this timescale can be a comfort. You don't need to worry about missing a crucial announcement while you sleep. The universe will move at its own pace. The data will accumulate grain by grain. The interpretations will evolve. Whether the first strong hint of life beyond Earth comes in 10 years, or 50, or longer, the journey toward that hint is already underway. In every spectrum recorded, every model refined, every careful paper on candidate biosignatures and planetary atmospheres, you can imagine all of those telescopes, current and future, as a loose constellation of metal and glass and code, scattered through space and on mountaintops, all quietly listening to the same faint stories in starlight. They don't hurry, they don't sleep, but you can. As this case file closes for the night, let the image of those observatories fade into the background. Let the idea of distant atmospheres, of biosignatures and careful investigations soften at the edges, until it's just a vague, calming sense that there is order in the way we're listening to the universe. Breathe in gently, feeling the air of your own planet fill your lungs. Breathe out slowly, letting the day go with it. Out there, alien skies continue their silent work. In here, you are allowed to rest.